While we are waiting, I will like to pass some instructions. Participants, please make sure that you have joined with your name following the naming conventions. It should be your actual first name followed by your last name. So please make sure that you have not joined with any nickname or any your device name. We will be sharing a feedback form near the end of this workshop. Please fill the forms so that we can get your certificates ready following the criteria of 60% of attendance time, which means you will be considered eligible for the certificates if you have attended this workshop for 60% of its time. Good morning, everyone. On the behalf of KSV and LDRP Institute, I warmly welcome everyone who has joined us in the workshop this morning. Let's have a quick intro about KSV and LDRP before moving forward towards the workshop. Kadi Sarva Vishwavidyalaya is a university established with Gujarat State Act 21 of 2007 in May 2007 and approved by UGC. The university has been set up by Sarva Vidyalaya Kelavani Mandal, a trust with more than 100 years of philanthropic existence to provide need-based education and develop courses of contemporary relevance. To be a university of excellence by providing research and skill-based activities and training which would foster higher economic growth and to provide education to all respective of caste, creed, religion, etc. LDI Institute of Technology and Research, Gandhinagar was established in 2005-2006 year. The college has been made steady progress during the past 16 years of its existence. As a prestigious state institute, LDRP ITR has long recognized its role in engineering education, generation, and dissemination of useful and relevant technological, industrial, and economical development of the country. The institute has contributed in the application of science and technology in the service of the society through different programs of international aid and assistance. And now, KSV and LDRP has brought to you the Break the Barrier event is a compilation of various interactive workshops from industrial experts, working professionals, experienced developers, CEOs, and more, where one can present your revolutionary ideas and skill up through a competitive environment presented by the hackathon to grab the opportunity to win exciting prizes. Among the 14 plus workshops, today we will be having an expert talk on quantum computing. And on that note, I would like to introduce our speaker, Mr. Sanjay Kumar, a research software engineer at IBM Research and the founder of Quantum Grad. Quantum Grad is one-stop solution for all quantum computing resources including news, articles, publications, jobs, and books. It is also a global content creation platform where people can read and write about quantum computing. Moreover, Quantum Grad also acts as a marketplace where people can submit information about their hackathons, publications, breakthroughs, etc., and publishes it on the website so that it reaches more people. So, without any further ado, I would like to hand over to Sanjay sir. Good morning, sir. Grateful to have you on board.
Yeah, thank you for the introduction. So I'll just start sharing my screen. I hope I have access to share the screen. Yeah. So is everyone able to see my screen?
Yes, sir, it is visible.
Yeah. So, good morning, everyone. As she said, like I'm Sanjay. I'm a research software engineer at IBM, and I'm a Qiskir advocate. And today we all are here to have a talk on quantum one-on-one, and we'll be going through what is quantum computing and why we need quantum computing and what is quantum software, quantum hardware, and some applications of quantum computing. And we'll be also coding out a Hello World program in quantum computing. So let's get started with it. So let's start with a basic question like why do we need quantum computing? So in this today's world, if someone is selling you a technology, even it's a object or something, even if I'm selling a pen to you, you might be thinking about like why do we need this pen or why do we need this technology? So let me ask you a question like how many ways I can arrange a dinner party of 10 people? So the answer would be more or less like 10 factorial, which is like 10 into 9 into raised to 2 1, and it is this many number of ways. So this problem seems very easy for a classical computer to solve, right? But what if I keep adding one more chair to this problem? So it will be like 11 factorial. But even if I keep adding more chairs, it will be 12 factorial, 13 factorial, 14 factorial. So soon the problem, which seems to be a small problem, will be converted into an exponential problem, which our classical systems are difficult to solve. So some problems are bigger than you think. But we already have like powerful systems that can easily handle big problems you might be thinking about right now. So this is the IBM Summit computer, which have like this many number of bits of storage, which is still not enough to perfectly model a caffeine. So the caffeine has only like 24 atoms, but modeling it requires a lot of power. Using a classical computer, perfectly modeling a caffeine would require 10 raised to 48 bits of storage, which is the number of atoms on the entire planet is 10 raised to 49, which is clearly an issue, right? So some problems are too small to clearly visible. This big and small, this duality of big and small is exactly where quantum computing lives in. Classical systems follows the classical law of physics. Quantum computer follows the law of quantum mechanics. Quantum mechanics is more or less like talks about like how things can behave on really small scale, which is very weird. I'll be explaining it why. And because of this, quantum computer can tackle really big problem much more efficiently than how classical systems can do right now. And yeah, let's talk about like a different perspective, like why do we think like quantum computer will be needed in the future? So what is the current situation in the industry right now? We all know that machine learning, deep learning, and all sort of things are in boom right now, right? And we all know like why it came into existence because of the availability of data and the availability of hardware. But if you look at the current trend, the machine learning algorithms are developing like every 3.4 months. But the classical systems, the hardware that we are building out doubles every 24 months, which is 7x slower. And this doubling of 24 months is called as Moore's law. And if you think about it, we are pretty much slower to catch up this rate. So one of the two possible solutions we have at this moment, the first is like to buy more NVIDIA GPUs and train it and burn more power, more electricity. Or the second option is to look for some other powerful architecture, and quantum computing seems to be a possible architecture for this. Second reason, data generation. We all know like how much amount of data we generate today. Deep learning and machine learning and all sort of algorithms came into existence because of the availability of data. Today, we generate 2.5 quadrillions of data. How to process this much amount of data and get a result? So if I give this much amount of data to a classical systems and tell that classical system, like give me the data in 10 minutes, it's difficult for a classical systems to give me a result. So to generate this much amount of data, to process it and everything, we need some kind of powerful architecture to do it. And quantum computer again seems to have a potential architecture for this. Now, why do we quantum computer even matters to us? So even the quantum computers today, like we are limited by certain parameters, but it remains identical to new paradigm in how we solve the problems. So quantum computer can provide us new algorithms, new approach to problem, new technological breakthroughs. So let's now talk about like what is qubit and why it is special. So, in classical systems, how we call as 1, 0 as bit, right? So in quantum computer, we also have a bit, but it is called as a quantum bit, and we call this as a qubit. So the Q is taken from quantum and the bit is taken from the data. So the name comes from its description. It's a quantum bit of data. So qubit is called a quantum bit of data. So qubit has some special property, which we'll be exploring in the next slides. And there are like different ways to build this qubit, physical qubits. It's similar to like a concept of making a bridge. They can be constructed differently, but with varying strength and weaknesses, but all serve the same purpose. So let's talk about the first property that our qubit process. So the first property is superposition. So imagine now you have 3 coins, okay? These are the 3 coins you have. And in the world of classical computing, what you will be doing, like each coin can be in the one state. It can be either head or it can be either tail, right? So this means that if I look out at the 3 coins at the same time, it can be in the unique order of the 8 unique orders, right? It can be head, head, tail, or it can be all head, or it can be all tail, right? But in the world of quantum computer, we have like a property called superposition, where each coin can be head and tail at the same time. Strange, right? Yes. So the coin can be head and tail at the same time. And this property is called a superposition. And with this property, I can see all the 8 combinations of the 3 coin all at the same time. Now, let me explain what do I mean by this. So let me explain this. It's more or less like if I want to see all the states of this all 3 coins, I have to run the program 8 different times to see all the possible states of 3 coins. But in quantum computer, I need to run my program only once to see all the 8 states of superposition. So this is an exponential speed up that we get to computation. So that's why like quantum computer seems to have an exponential speed up over classical systems because of the property of superposition. So for n raised to qubits, we'll have 2 raised to n gates. So let's talk about the second property, which is called entanglement. So it's a pretty difficult topic to understand. Even Einstein was confused about it, explaining it. So remember how I said like quantum mechanics can be weird at separate time, right? So this is one of the weird thing. It's hard to describe like what's going on, but even Einstein was surprised, as I told. He called this as a spooky action at distance. So essentially, like 2 qubits, 2 bits of quantum data we take, and we make them entangle somehow, and they like are correlated each other. And even if we separate them apart, like even if I keep 1 qubit in China and 1 qubit in India, I know something about the other qubit. So when you observe the one, you learn something about the other, no matter how far it is. So even if the 1 qubit says I'm head, the other qubit will also say like I'm head, even if I keep them universe apart. So that's the second property that we use in quantum computing. It is called entanglement. Now, so till now I have covered, I'll just brief summarize like whatever I have covered till now. And if you have any question, feel free to interrupt me in the middle of the session. So the quantum computer uses a special bit of data, which is called qubits, which allow us the law of quantum mechanics. We use this law to our advantage, enabling us to put quantum computing into superposition or to get entanglement. Using these techniques, we estimate a quantum computer would be requiring only 160 qubits of to model a caffeine, which is much more manageable than 10 raised to 49 bits of classical bits. So now let's look at like how a quantum computer looks like today. A chandler. So the quantum computer IBM looks like a big chandler, full of cable for sending data and maintaining the environment. At the very bottom of the quantum computer, so this all golden thing is the wires and all connection, but the quantum computer is at the bottom. So very at the bottom is the quantum processing chip. It's about size of a stamp, like a postal card stamp. So it's very small. So it lies at the bottom of the quantum computer. So if we zoom in this processing chip, so it will look like this. So the dark blue squares you can see are the qubits, are quantum coins that we talked about in the future slide, in the present, in the past slides. The swiggy lines are the microwave resonators, in which we talk like how coins talk to about each other and how we superposition and entanglement them, and we send instructions about them. To work properly, this quantum chip needs to be kept at a very cold space, and it is more or less like 0.015 Kelvin. So for that reason, you will always see quantum computer will be enclosed in a dilution chamber. This white color thing is called a dilution chamber. So you will never see a quantum computer like lying outside, like in air or something. No, quantum computer needs to be kept at a very low temperature, at a very low temperature. That's why like they're always enclosed in some kind of glass chamber or a dilution fridge or something. So this is a quantum computer at IBM, and this is one of our scientists that is making quantum computer. So now you might be thinking like if quantum computers need to be like kept at this much temperature, then how a people can access it, how people are able to access it via classical system, via our laptops, via our classical systems like PC and all sort of things. So this is a small video for how we are making quantum computer accessible via cloud. So this is the classical systems. You make a quantum circuit and you send across to IBM. Then IBM systems converts this classical signals into pulses. Then these pulses are being sent to quantum computer. Now the quantum processor chip that I talked about will be processing this information. And the pulses from this quantum chip will be sent across again to IBM systems. IBM systems will be again processing these pulses into classical data, and this classical data will be presented to a computer. So this is a process that we follow at IBM to make quantum computer accessible via cloud to all the classical systems. Now, some people might argue like we don't have that much applications right now, but we do see a future of quantum computer, and I'll be talking about certain applications of quantum computers where I believe like quantum computer can be used out is the finance. So first thing I'll talk about is the finance. Like the banks are using quantum computers. They are trying out quantum computers to optimize a lot of portfolios of the client, where they can detect fraud and all sort of things by doing a lot of optimization. The second thing is the random error search. So in a huge table, we can actually search for an element using Grover's algorithm, which will be like giving up a quantum speed up. So instead of O of n time complexity, we'll be having O of root n time complexity. It is more or like a quantum speed up that we'll be getting out in searching an element for a database. The third is chemistry, which I talked about, like caffeine moleculation or simulating any chemistry and like taking out different proportion of drugs and making optimization of that and thinking about like how we can make a proper drug from that. So there is application in chemistry as well, and there's an emerging field of machine learning. It is called as quantum machine learning, QML, where we are trying to run the machine learning algorithm on quantum computer, where we do some encoding and decoding of the data and try to run the algorithm on quantum computer. So there is an emerging field called quantum machine learning, which is coming up. Then there is one more application called encryption, period finding, where there's a hype going on that we might be breaking the RS algorithm. So this is a factorization algorithm. By Schwartz algorithm, we are able to find the period of the algorithms in encryption. Third, the last one is the quantum tunneling. This is more or less like a 6 topic that are presented, but there is the more number of applications in batteries, car batteries, and all sort of things. So we have in manufacturing, and we have a lot of applications, but in this slide, I've just presented 6 to you, the future of quantum computing. Now, let's look at some other quantum gates. So just like classical systems, how classical system have gates, like how you make half adder circuit or full adder circuits or any circuit in classical systems, we do have a gates in quantum computers, same. So first gate I'll talk about is the Pauli X gate. It is it just flips a qubit from 0 to 1 or vice versa. So you can imagine this Pauli X gate more or less to the classical NOT gate. It just flips, right, 0 to 1 or 1 to 0. So we call it as a Pauli X gate, and in classical system it is called as NOT gate. Then the second gate I will talk about is the Hadamard gate. It just puts a qubit into superposition of states. I talked about, right, how a coin can be 0 and 1 at the same time. So this is the gate that is used to put the qubit into that state of superposition. So it is called as Hadamard gate. The third gate is the control NOT gate. So it is basically it flips the second qubit, which is called as the target qubit. Only if the control qubit, the qubit 1 is 1. So if it is 1, it will flip it. If it is 0, it won't do anything to the target bit. So it's more or less called as control NOT gate. It is called as C0 in quantum computer. So whenever you are learning any programming language, be it Python, be it Java, or any programming language, and any language, it has a hello world program, right? So in quantum computer, we do have a hello world program, and it is called as Bell state. So this Bell state is considered as hello world program in quantum computer. So what is exactly Bell state? So Bell state is a specific quantum states of 2 qubits that represent the simplest example of quantum entanglement. Remember how I talked about the entanglement where one qubit will be entangled to the other qubit, and if one is head, the second one will be also head. If the one is tail, the second one will also be tail. So we'll be demonstrating this, how we can do this, how we can do the qubits entanglement. So the H gate puts the first qubits in the superposition, and C0 gate just both flips it or doesn't flip the second gate based on the Q0. So if Q0 is 1, it will flip the qubit, and if Q0 is 0, it won't flip the qubit. It's basically a control and target qubits. Now, assuming the qubit starts at 0, so irrespective of anything, all the qubits starts at 0. But when measured, they will be only like 1, 1 or 0, 0, but they cannot be 0, 1 and 1, 0. Because qubit 0, if it is 0, it will be flipping it to 0, and if it is 1, it will be flipping 1. So the output will be like 1, 1, 0, 0, but it cannot be like 1, 0 or 0, 1. This is the entanglement, simple entanglement that we do. And this is a circuit that will be building out actually, and will be executing the circuit in quantum computer, and we'll be seeing what results we can get and what are the errors that we'll find out in that. So I'll be proceeding to the live session, like how we can actually code out a quantum computer. But before moving to it, if you guys have any questions, you can ask me now before moving to the live demo. Or if you don't have any questions, I'll just move out to the live session. So I'll just move to like how we can actually code it out. Okay, so so there are like two ways how you can actually code out a quantum computer. So you can actually install Qiskit to your local systems, or you can we have a IBM website where you can actually go and actually start quantum computer coding. So you just need to go to IBM Quantum Experience. And if you click to the first link, IBM Quantum, there you can, it's freely accessible to everyone. So everyone can join this, and they can just sign up and you're good to go. So you can just click on Launch Lab. So once you click on the Launch Lab, a Jupyter Notebook will be spinned up for us that we can actually use it for. So you can just click on New File, New Python, and we have a Jupyter Notebook ready. So first step, so Qiskit uses Python. So I think more or less like for learning quantum computers, we don't need to learn some new technology or new programming language or something. No, it is simple Python that we use, and how we install NumPy, Pandas, and all sort of things like different packages. It is similar. Like we have a package called Qiskit, which is used to run quantum computers. So we'll do just from Qiskit. Qiskit is our quantum library that we use. It's a module that have all the functions that are necessary to run the quantum computer. So from Qiskit, we'll just import star. I hope everyone is able to see my screen. Okay. So I'll just do from Qiskit import star. So I'll just import all the necessary functions that I'll be needing for this. So let's start by building out simple quantum register. So if you want a quantum register, you can just do quantum register. And since Bell-State has 2 qubits, I'll take 2 quantum register. And I'll also take a classical register to take the results out from quantum computing. So now, if I want to build a quantum circuit, it's a simple instruction that I need to do. It's called quantum circuit. I just have to write quantum circuit, and I just need to pass my quantum registers and classical registers. My quantum circuit is built. Now, at any moment of time, if I feel like I need to see my quantum circuit, like how quantum circuits look like, I can do qc.draw. And I can see my quantum circuit. So this qc.draw function, you can call out any moment of time if you want to see your quantum circuit. So as you can see, I have taken two qubits, 2 quantum registers, Q0 and Q1, and 2 classical bits for taking the results of quantum circuit. And I can simply build out a quantum circuit by using this quantum circuit argument. Now, since the Bell-State, I told like the first Q0 we need to put in the Hadamard gate. So for applying Hadamard gate, I can just do qc.h, and that stands for Hadamard, and I need to apply to qubit 0, so I'll put 0. So Hadamard gate is applied, and again, if I want to see my circuit, how my circuit looks like, I can just do qc.draw. And I can see like QC has the circuit Hadamard gate applied. Now, the next gate that we applied was a C0 gate. So I can just do CX, and the control bit was 0 and the target was 1. And again, I have applied the gate, and again, I can draw QC.draw. See, it's very simple to draw, to build out a quantum circuits and all sort of things. So I have applied C0 gate as we show, as we seen in the previous slides. Bell-State is made by this. And now I just need to do qc.measure, because since I need to take the measurements of the qubits on the classical register, I can just pass I need to get the classical quantum registers to my classical registers, and I'll do qc.measure. And again, if I want to see my circuit, I'll just do qc.draw. And now our quantum circuit seems pretty much ready. Like I have applied Hadamard gate, I have applied the C0 gate, and I've also applied the measurements to it. Now, there are 2 things before running this circuit. So this circuit, since quantum computer, you know, right, it's an expensive process. Like it goes to the queue and all sort of things, because a lot of people are using this quantum computer. So before sending this circuit to the actual quantum computer, we actually run it on a simulator to verify the circuit, like if the circuit is working fine or what is the output of the circuit. And if we are satisfied with the circuit, like if the circuit is correct from the simulator, it's a classical simulator, and then we actually send out a quantum computer. So let's run the circuit on a simulator first, and then we'll be sending out to quantum computer. So to take the simulator, we can just take it in a variable called backend, and we can do AER.get backend, and we'll be taking AER simulator. So now our backend is ready. And if you just want to execute a circuit, if you want to just run the quantum circuit, you can just use the execute function, and in execute statement, you can just pass your quantum circuit, which is QC, and which is the backend that you want to run. And I've already defined my backend app, and my job is executed now. Now I'll just take my results in a results variable, and it is just done by job.result. And now if I want to plot this histogram, I want to see the results of this quantum circuit. What is the result actually? I can take a module, Qiskit, from qiskit.tools. I can import a plot histogram to see what is my histogram of the results. So now on this plot histogram function, I can just pass my results, and I'll just take the counts. So now, since now you can see our result, this is the result that we got from a simulator. We run this circuit on a simulator, and we got the output as 0, 0, and 1, 1. So this, how we do is more or less, we run the circuit multiple times, and we get a probability of 1, like 50-50%, and which shows the answer of us, like it's 0.49 and it's 0.59, which is approximately 50-50, and we get 0, 0 as the 1, 1 as the result. And this shows like it's an entanglement, like if qubit 0 is 1, the other qubit is also 0. And if the qubit 1 is 1, the other qubit is also 1. So this is a perfect example that we have of entanglement, and we are satisfied with the circuit, and the circuit is running perfectly fine. And now we'll be actually sending our circuit to real quantum computer. So to use your real quantum computer, you need to do IBM-Q.load account. This will be the statement will be loading your account, which you will be using, which you have used for signing in this IBM Quantum Lab, which is free for everyone, and everyone can sign up and they can start using quantum computers for free. And then I can just take a provider, which will be my provider will be IBM-Q. And then again, now in this case, again, I'll take a backend, but the backend will be a real quantum computer and not a simulator. So I'll take from provider. I'll take one machine, IBM-Q. Q2. This is the name of a backend of a quantum computer that we have at IBM, and we have multiple devices. We can use any of the machine. So now again, the same process I'll repeat. Again, I'll make a job variable, and I'll again do the execute statement. And again, I'll pass my quantum circuit, which was in QC variable, and then again backend. I'll just backend is equal to backend because I've taken the backend, the real quantum computer, in my backend statement. And now this job has been sent to quantum computer, but to just 1 minute. Okay, so we need to pass QC quantum circuit. So now this job actually has been sent to quantum computer, and to see the status, like whether it is executed or what is the status, it is queued, it is executed, or the job is finished, we have a module called job monitor. We can use it from Qiskit tools.monitor import job_monitor. So now in this job monitor function, I can just pass my job to see my status, and you can see my job status is queued. So that means my job has been sent to IBM Quantum Computer, and it has been queued. So, and you can see the number. So it is 5, and it will take some time to the process to get to this queue. So similarly, like you can check the status after some time. So that's why you make sure that on the quantum computer, on the classical system, on the simulator, our circuit is running fine. And then we send out to quantum computer so that we don't waste a lot of time. To save the session time, I have already made a backup session where I've already executed a circuit on a quantum computer and the result has been come back. So I'll just explain here like what exactly things were going on. So once your job has been successfully executed, right, you will be seeing the status as job has been successfully run. And then again, we can do result, which is like result is equal to job dot result, and we can get the result. And again, we can use the plot histogram function, and we can do result dot get counts, and we can again see the counts. And this is the result of running the circuit on an actual quantum computer. So now one might think, like one might question me, like you said like the output should be 0 0 and 1 1. But now in your real quantum computer circuit, I can see the result as 1 0 and 0 1 also coming in the picture. So this is something we call this at a quantum error correction. You might be have heard about like there's a lot of errors that we have in quantum computers, and day by day we are improving our errors, like how we can minimize the error. But since and for this reason, we run our quantum circuit multiple times, and this circuit has been run thousands times. And this 1,000 times we have compiled it into a probability of 1. So if you measure, if you add like 0.48 and this, the probability will be 1. But if you take the highest probability of out of all this 4, you can easily make out that the result was 0 0 and 1 1, and we can actually ignore this 0 1 and 1 0. So with the highest probability, we can actually make out the result. And this is something that we call as error correction and quantum errors. And we have a lot of things that are coming up called quantum error corrections. And this was the simple Bell state that we actually run on a simulator and then on a quantum computer. There was something like too technical, but trust me, like it's not that difficult, and you can actually run. If you know Python, you can actually code out a quantum computer. So this was more or less about like how we can actually run a quantum computer. And this was the session about this. And I just want to say like anybody can learn quantum computer, and it's not like a physics people can learn quantum computer or a math guy can learn quantum computer. No. Personally, I'm from electrical and computer background, and I too love quantum computing, and I just learned. So quantum computer, anybody can learn. So irrespective, you are from mechanical engineer or you're from computer departments or you're from electronic background, anybody can learn quantum computer because it's for everyone. And it's more or less like we are in a very early stage. So we need people from different fields to come up with the different use cases of application so that we can explore quantum advantage and we can actually explore quantum computing more and get a real benefit from quantum computers. And lastly, I want to talk about my startup as a bonus about like what is Quantum Grad. So there is a website that I have built out. It's a Quantum Grad where you can actually jump in and you can find all the latest articles. So we have a lot of articles related to quantum computing. So a lot of people can come and write and read about their experience. So some people has written about their Qiskit advocate journey or the Womanium event, or somebody's talking about quantum architecture. So you can just give a read and you'll get a lot of information from there. And you can also get all the latest news, like what's going on in the current world about the quantum computer. You can come and just read a lot of news, publications, what are going on. Then certain events, if you wish to attend, like there is Quantum Game Jam is coming up. There's this hackathon is coming on. This career fair is going on. There's a lot of events coming up. You can get updated from here. Then if you are interested in internship or if you're doing in some full-time in quantum computing, you can come here. You can see there's an intern position open up here, which is remote, and there's a full-time jobs and all sort of things you can get. So basically this act as like a one-stop solution where a lot of people can come and just explore a lot of things. Then the books, there's a lot of books you can explore about quantum computing. And we also have our YouTube channel where they put a free content like videos and all sort of things we explain for free. We don't charge any money for that, and we just explain there. And we also have our Instagram account where we post 1-minute reels to explain different quantum computing things. And we have different quizzes, and we make some quizzes on the Quantum Grad stories, and people can come and just answer a lot of questions. And we also have a giveaway going on right now where we are giving quantum computing books to everyone. You just need to come to Quantum Grad and just sign up here, and you'll be receiving the weekly newsletters. Like every week we send out all this information. You can see on the website all the latest information to your mailbox. So you just need to come and sign up, and you just need to write one article, and you'll be good to go for the giveaway. And this giveaway includes like career advice of quantum computing, mentorships, research paper opportunity with me, and mentorships and a quantum computing book. So that was more or less about, and we also have a Discord server that I'll be sharing the link with you all, where you can join. And its Discord server have a lot of mentors, where if you want to start your journey in quantum computing, you can join the Discord. You can ask a lot of questions where the mentors will be helping you to get started with quantum computing. And I think yeah, if you have any questions, I'll happy to take all your questions now. And so if you want to contact me on LinkedIn or your email. And now I'll take all your questions, whatever you have.
Can you read chat section as we have few questions there?
Yeah, I just wonder where is the chat section? Yeah. Okay. So first question is how we can commercialize this technology. Can superposition disclosure back blockchain census verification as both bad chain and good chains will see correct? The communication via quantum computer IBM will be dependent on internet connection relay. So it's more or less like all technologies will get disrupted by quantum computing. It's not like quantum computer will be replacing something or something. No, quantum computing will be disrupting both blockchain, machine learning, or all sort of thing. Because think about it as a thing like what are hardware used for? We need to compute, right? We need to compute fast. If I give you 5 GB of data, give me a result in 5 minutes. It's the underlying hardware that makes, right? Why we are using AWS cloud and all sort of things? Because cloud, they are giving a faster results. They are able, like they are having a good hardware. So it's more or less we are running all the same, like we are doing a lot of computation, and quantum computer gives exponential speed up on the computation. So yes, there's a lot of technology that will get disrupted by quantum computers. And yes, like everything depends on internet connection, because since I mentioned like quantum computers, it's not something that we can install like in every home, like how we have the classical systems right now in every home. So that's why like we need to make it up somehow by the cloud technologies, so that each and everybody can access quantum computers right now. I hope that answers your question, and if something doesn't answer, like feel free to unmute and ask. The language to access quantum computer will be C++ or any specific language by IBM. So for IBM, the quantum computing language that you need to know is Python. Since I coded out everything is Python, it's just you need to know Python about it. And Python is very simple language. It's not something like that has a high learning curve. You can actually learn Python, and you can start coding out quantum computers. Okay. So how to become an expert in quantum computing? So you need to get started with quantum computing. So there's a lot of resources out given by Quantum Grad. You just need to join the Discord server, and on the Discord server, you can just get started with quantum computing. And more or less, I would recommend to do some internships and get collaborated with any professors and get some quantum experience, quantum project experience in your resume, and just get started. Like I strongly recommend like just get in touch with a lot of professors to get started with quantum computing, because they have a lot of projects, and it's a good way to get some experience on a resume. So that will be the first advice that I'll give you if you want to like go into quantum computing field. And can you give any scale input to current quantum computer? I did not understand. What do you mean by scale input, Shrikant? I did not understand what do you mean by scale input to the current quantum computer? So Shrikant, if you want, you can like unmute yourself and tell everything works fine.
Hello. Are you able to?
Yeah, I can something hear you about.
Okay, sir. I means in professional terms, suppose I want to give any input, like suppose I am trying to simulate something for a financial, and whatever the input that I am having a giant scale, can I give it to a current scale computer?
Yeah, so it's more or less depends on, we have like so in classical systems, you know, right? Suppose just to consider an example of machine learning. Okay, so machine learning, if you want to give some output, right? Like suppose it's a language model, and you need to give it the words. Like you want to train it on the words, sentences, and paragraphs. How you'll train? You need to somehow like decode it, right? You need to encode the output, and like center, like we need to use some tokenizer things and give input to the model, right? The quantum computer is more or less similar to that. You can give all your output, but we need to encode it so that quantum computer can understand. So we need to process the input in such a way that quantum computer can digest it. So we can give your scale output, and given the finance example, there's a lot of finance model that we have in quantum computers. I can share you the link later where you can give a read to it. So we have a lot of finance model where we give a lot of data to quantum computer, but we do a lot of processing of the data before giving it to the quantum computer. So yes, we can give any scale input, but you need to make it in a proper form that quantum computer can digest. And can we have an internship under your guidance for quantum computing plus blockchain? So more or less right now, under me as in like in IBM, more or less. So we have recently opened up the internship position. It was not for quantum computing plus blockchain, but it was more or less related to quantum computing. But unfortunately, the position had been like closed up. But in future, if something comes up from IBM internship, I'll be just posting out as a story on the Quantum Grad Instagram channel, Instagram account. So you can just be up to date with that internship position. I just whenever internship comes up from the IBM side, I just posted out a story on just on the Instagram, and you can get to a lot of things, or you can just monitor the job section of our Quantum Grad to get a lot of internship. And there is an artificial brain company in India. I think they are hiring for research intern, and it's a remote position. So if you are interested, you can join that company as well for internships. So let me know if if some other questions I did not answer properly, I can take more questions if you all have. And I know quantum computer seems to be like very difficult topic right now, but trust me, it's not that difficult. It just you need a proper proper guidance, mentorship, because right now today there's a lot of resources out there, and some resources are too high level, too advanced, and by looking at that resources like few pages, you feel demotivated and you just cut off the part there. But don't do that. Just join the Discord server, and we'll help you out, because there's certain ways that you need to go like step by step and not go to the higher levels. You can go step by step and solve maths, linear algebra, and sort of things. It's not that much mathematical also required, but yeah, maths compulsory for that. You need to learn linear algebra and sort of things. And it's not that difficult to get access also. Like you don't need to pay for quantum computer usage. IBM has free quantum computer access to everyone, where I think it is limited to 5 qubits machine you can use for free. So it's just like a lot of resources are available. It's just you need to come up and you need to be passionate about doing it, and you will be able to do it. Yep. Okay, Discord server link. So this is my Discord server, where we have different channels like announcement, welcome, and we have community where we talk about, and if there is some events coming up, and there's a Qiskits, like we have IBM has a Qiskits developer examination as well, where people can and right, it's a certification provided by IBM for quantum computers. So we have a link for the channel for that as well. We talk about jobs, we talk about news, and we talk about quantum gaps, like what is the gap that is there in quantum computing. So we talk about a lot of stuff here in the Discord channel. I'll just share this link. Just to yeah, so this is the Discord server. Just join and ask all the questions that we have, and we have mentors there, and we'll be able to help you out. So the proper use case will be the modeling time is more or less, take an example of quantum machine learning. So in quantum machine learning, we're trying to get some sort of things, or get some more accuracy or something. We have a chapter on Qiskit. I can share that with you. So we have a quantum machine learning documentation here on the Qiskit. I would recommend, like if you are interested in that, you can just join this one. Yeah. So this is one of the example that you might be looking into, like just give it a read, like how we are trying and what we are trying. This is open and like torch and all sort of things it's being used here. Like it's a big topic. You can just give it a read in your free time. And if you have any questions, get me out on the LinkedIn and I'll help you out. And let me know if you have more questions or any of the material you want to explain me about the slides or something. If you did not understand, I can go over again. Like feel free to have all the conversation, be casual, it's okay. You don't need to be like a professional for asking questions. You can ask any questions if you have. So I think we have done more or less all the questions, and yeah, so I think we can wind up maybe, because quantum computing is more or less like it's a vast topic, and explaining a lot of term in the first lecture, in the first thing, it's not a good idea always. So always start from small things, and go ahead with small things in quantum computers. Yes, quantum computers can be used to decode that. Yes. But it's something that, for decoding all sort of things, we need higher qubit machines. And the maximum that we have right now is 127 qubits. It is called IBM Eagle. We have, and it is 127 qubits. So we need more powerful quantum computers, more number of qubits, and to solve the problems. But currently we are limited by the a lot of limits are there, like limited by the number of qubits, quantum error corrections, and hardware things, and a lot of things we are restricted, but day by day we are improving.
Sir, actually programming with the quantum computer is like creating a circuit in a program, creating a program in a hardware way. So can scale from 127 or 129 bits up to 256 bits or something, or IBM doing that research on that direction? Or
yeah, so more or less, Shrikant, what is the thing, if you think about, like, if you can build a machine of 5 qubits, like if you can build a system of like 5, you might be thinking like I can double down, like and make 10, 15, 20, and we can make out, right? Like if I can make like 5 qubits machine, then why I cannot make 100 qubit, 1000 qubit machine? So there's a lot of coupling things, and there's a lot of errors that we get. So as we go the higher number of qubits, the error keeps on increasing. So we need to think about like how we can minimize that error. That's why, like in this year, we have a plan of releasing a 432 qubits machine, which is called Osprey, and we'll be releasing it soon. And so that will be the machine. And it's more or less, we are limited by a lot of quantum errors that we are trying to solve out. We are trying to minimize a lot of errors. And since I mentioned on the circuit, right, a simple bell state also gives that error, like a 1, 0 and 0, 1.
okay.
So if a simple bell state can give that error, suppose like if you're running a big circuit, that will give how much amount of error? Though we have exponential speed up, but we have exponential errors as well that we need to figure out. So coupling more qubits, like topologies and all sort of things, makes us difficult to scale up in the level that classical systems can do.
But this is actually giving, suppose consider a RSA or something. The algorithm that to crack it is taking years will be converted in microsecond, or it will giving cracking that algorithm microsecond or second. So the level of scale up, it means the amount of the efforts that increasing in qubit would be beneficial to the humanity, because consider the case of in chemical section, suppose protein creation, or in pharmaceutical drug creation would be like 1,000 of simulation could be done in a second. So in epidemic situation, it would be much more helpful to the humanity.
Yeah, so that's what, like quantum computers will be used for, like more or less for the optimization. So think about like if I give you like 20 chemicals, and I give you like take 5 ml of this, 5 ml of this, and this, and calculate all the possibilities, and give me the result. That's what like our classical systems fail. Suppose I want to go from distance A to B. Okay. So if there is only one path, classical systems can compute, right? I want to go to A to B. But what if I say like reaching from A to B, we have waterways, we have roadways, we have airways. We have 3 ways to go. Okay. And you need to find the optimal way, like how I can reach from destination 1 to B. Then there is a lot of optimization. And on top of that, if I say I need to visit an hospital with this number of doctors, I need to have a gas station with only this quantity or this quality of petrol. And if I keep adding constraint to it, and from reaching destination A to B, our classical system takes years and years to solve that. And that's where quantum computer comes into picture, and they can try all the possibilities and do a lot of optimization and will be able to get better results.
Thank you.
So yeah, all your chemical things and all sort of things are correct. Like, yeah, it will be helping there a lot. Yeah. So yeah, let me know if you have like more questions, like feel free to ask any questions. Like I know it's like a weird topic, but you can ask, and I'm happy to answer anything, any doubts, like feel free. Even if it's like numb question or anything, ask anything, doesn't matter. Question is question at the end. Or if you don't have any questions, like you can wind up now, and like you can later come back to me on the Discord server or on the LinkedIn. I'm happy to answer all the questions. It's more or less like whatever data structures and algorithm you need to for classical systems. It's nothing new that we are using. We are same using Python. We are using everything, same coding language, same data structures and algorithm required to build a queue. Like you saw queue, right? The queue state was 5 and all sort of things. It is pretty much same. And same data structures algorithm. There is nothing new that we have built out, and for the programming side, nothing new we have built out. It's just we are trying to integrate the hardware of the quantum computing with the classical system. So same, it is nothing new data structures, like a new data structure has been released for quantum computing. No, it's same Python language. There's nothing new. Whatever data structure algorithm you require for classical systems, it is same. It's just you need to get the basics of quantum computers and how we can build out a different circuits, mathematics, and yeah. And this Qiskit textbook, it's a great start because it's a free from IBM. You can just go to Qiskit source and you can just click on get started. Then this is all the textbook. Like you can get started on the since I mentioned, right, you can install the module on the locally. You can just install locally or on the cloud, which I just demonstrated. Like you can just go to IBM Quantum Lab and you can install the source, and there is a lot of things like introduction to Qiskit. You can just start using this book and coding out. It's nothing new that you need to know. Yeah, there's concepts and all you need to know, but data structures and all, it's pretty much same. Okay.
So ultimately, in order to use this computer in a better way, we have to represent our data in such a way that computer can understand and give the result. So our task is to just using a classical algorithm, our task is to just represent in a way that computer can understand. Will it be like that, or should we have to shift our paradigm in different ways? Our thought process in a different way in order to just communicate with it.
Yeah. So yours are partially correct. So classical systems, consider classical systems. If you're typing a text message on your phone, how the classical systems is able to understand, you're actually decoding into 1 0, right? In the back end. Classical systems can only understand zeros and ones. So you're actually decoding that. So in quantum computer also we need to decode, but quantum computers are like special purpose quantum computers, Srikanth. So no one can actually like so suppose I'm multiplying two numbers. Okay, so I'm doing 2 into 7. Okay, so answer is 14. If I run this 2 into 7 on a classical systems, it will just run it in microseconds maybe.
Yes.
But if I give 2 into 7 to a quantum computer, it is worse perform. It is worse than classical systems as well. So quantum computers are more or less like a special purpose quantum computers which have certain algorithms where we can use it for some special purpose. It's not for all the purposes that we'll start using quantum computers. No. Classical systems will be there and we'll be using it for a normal day-to-day tasks. Quantum computer is something that we'll be using for some different purpose, some special purpose, like optimization, like searching in a database, period finding, quantum machine learning. So there are certain use cases of quantum computers that we need to understand. It's not like quantum computer we can use it everywhere, because quantum computers, I told, right, it has some restrictions, and it will give some new paradigm, but it has some new algorithms and all sort of things that we need to follow. So it's a special purpose quantum computer. So quantum computers are considered as special purpose quantum computers and not general purpose quantum computer.
Okay. Thank you.
Discord link, I can, sorry. Just 1 minute. Here you go. So, Preet, you can get a Discord link. I just posted on the chat. So yeah, I think it was a great, like, nice time with everyone, and I love speaking with a lot of people. So it was an amazing session, like with the Q&A, and I'm always like available on LinkedIn. So yeah, thank you everyone.
Thank you, Sanjay sir, for presenting such an awesome session. It was really very wonderful learning experience. So let's conclude the workshop. Thank you guys for attending.
Thank you everyone. Bye-bye. Take care.
Enjoyed, and we look forward to seeing you in next events as well. We have shared a feedback form link. Please fill the form to tell us how much you like the workshop or if you want us to improve in any aspects. The form will be followed by your details using which we can get your certificates ready. So please make sure that you fill the feedback form. Please join the Discord server as it is mandatory so that you can get further information about the hackathon. And stay connected with our social media to stay updated. That's it. Let's end the talk. Bye everyone. Have a good day.